All right, welcome back. Thank you everyone for coming back. We are in the last half day of the last day of IRA. So if you're here, that's very good. You should be proud of yourself. We are going back to our invited speakers, and it's my very great pleasure to introduce Professor Georgia Chalvatzaki. Georgia is a full professor, congratulations, for robot perception, reasoning, and interaction learning at the Computer Science Department of the Technical University of Darmstadt and Hessian AI. Before that, she was an assistant professor since February 2022, an independent research group leader for March 2021, after getting the renowned Emmy Noether Program Fund for the, a lot of awards, renowned Emmy Noether Program Fund of the German Research Foundation. The project was awarded within the ENP Artificial Intelligence Call of the DFG. Only 9 out of 91 proposals were selected for funding. Very well. It enables... No, you won all of these awards. We need to acknowledge them. Yeah. It enables outstanding young scientists to qualify for a university professorship by independently leading a junior research group over 6 years. Wow. All right, so this is going to be an amazing talk. Help me congratulate.
I hope so. Now you raised the expectations a lot. Wait,
Help me welcome Georgia.
Not working. Let's see. Okay, there it is. Okay. So, hello everyone. I'm really humbled to be to be invited to this workshop and among these amazing people, speakers, etc. So, I will try to give you my brief take on long horizon manipulation. My goal in my lab is to try to advance research towards mobile manipulation robots to allow them to enter in our houses. So, a large part of our work has to do also with integrating perception and coordinating robots, but reasoning and planning has a huge part in it. And if we look into how humans, even from a young age, start interacting with objects, they understand their functionalities, and they are able to create plans and put things together, even if they might have combinatorial compositions, they are still able to reason about them. And this is quite challenging for robotics. So as I said, my goal is to advance. I guess many people are trying to go into this direction to make robots like Rosie the robot here being able to set up the table, not exactly like this, it would be nice, because then there would not be so many combinatorics, but essentially we know that even the household tasks that are so simple, they are very difficult to be solved. And what we have now is, we are not so bad, right, in the mobile robot domain. We have now these robotic waiters in Japan. You might see them also in some airports and so on. But the problem is that they don't do manipulation, because effectively navigation and planning in environments even among obstacles is a, let's say, easier problem relatively compared to also having to solve manipulation tasks, having to reason about different combination of actions so that you can achieve a long horizon task. So yes, there are a lot of challenges, and I guess you have already discussed a lot of them. So the complexity of the tasks and the horizon is one big challenge. The need for complete state domain specification, problem specification are big issues. The need to account for these long-term consequences and how, for example, we could be reactive. We need to generalize, we need, as I said, to be reactive, and there is also a computational overhead to be considered, and many, many others. So if we look at the field, there are the classical approaches that go to task and motion planning, and in the last, 5, 6 years, we also see several learning-based approaches that try to tackle this problem also in an end-to-end fashion, and it becomes like a crossroads. But I think that we will discuss that the best way to view this problem is basically that they come back together, and eventually what we can see and start discussing how we can effectively learn for task and motion planning. So in this talk, I will try to give you some insights about our research in the last couple of years of how we could have more efficient task and motion planning by deploying learning to accelerate the search of classical task and motion planners, how we could deploy maybe LLMs together with PDDL task planners in order to create more domain agnostic interactions, and especially if we consider humans giving problem specifications that do not directly translate to PDDL problems. And finally, we will see an approach that combines guidance from planning to learn how to solve combinatorial problems like assembly tasks. So let me get started with the first topic, where essentially one second, yeah, here we are. So essentially, we started looking into task and motion planning some years ago, and we easily found out, like pretty fast, that there are a lot of planning dead ends that may arise from the fact that you start by single symbolic task plan solutions. So of course, there are the options of replanning and so on, but what we wanted to see is whether we are able to provide a vast variability of possible task skeletons, such that we can enable a more extended search during a single planning optimization approach. And for that, we introduced extended TAMP, which uses top K skeleton planning in PDDL streams for an optimal extended search over plan skeletons and compositional operators, which means combining both discrete and continuous decisions empowered by the PDDL stream formulation using upper confidence bound trees, or else UCT. So let's look a bit into this problem. So effectively, you may see it like taking PDDL stream and top K planning and formulating it into a Monte Carlo tree search approach with progressive widening. So as I said, we start with the PDDL stream formulation, that you have some object starting goal configurations, actions, and streams. Streams are basically black box samplers, let's say, that they can give you additional objects, and they can effectively lift, in some sense, the problem into the continuous space. So if we look at possible plans, we took advantage of planners like SimK, that is a top K planner, in order to generate possible plans. Here are some possibilities of plans for a simple toy problem where we have these two objects and we want to move, we are allowed to do only top grasps, and we want to move the green box to the right area here, but the robot has to figure out that it has to first move the red one, take it out of the place, and then move the green one. And there are different possibilities of how to do this, effectively combining it with the correct geometric information so that you can effectively sample correct grasps and so on. So how does this look like? So we start from an initial route, that it is an extended route because it samples many possible top K plans, and we do UCB. Basically, we solve it as a multi-arm bandit problem on the root node for doing a skeleton selection. Obviously, we have defined also some reward function that allows us to guide this selection process. Then, as every Monte Carlo tree search approach, there is a decision stage and a transition stage. In the decision stage, we have to do some specific decisions, for example, which are the grass poses that we want to select, again with UCB, and then we do the transition, so we execute the transition using streams, for example, if it is to execute a grasp using some RRT or any kind of stream-based black box generator. So this is how it, let's say, looks like, the tree search. Effectively, when you find, for example, some action that is not feasible, you stop the tree search and you don't spend any more computation time into this problem. What is also very interesting is that since we are learning a Q function, we can use this Q function as a way to stop the tree search even in task plans that we have not already visited it, so we can effectively reduce the search time by doing this trial and error approach and speed up the planning process. So some problems that we looked into, for example, here we have this regrasping problem where we, in theory, sense with an external camera the object, and we can only get grasps through this sensing approach. We have the constraints that we need collision-free motion. We are able only to grasp in 5 directions, and as I said, depending on how the object is seen by the camera, we can sample some very respective grasps. And what we want to do is to put it upwards on the up self here. Another problem is the 3-body scenario where we want to effectively remove the green box, allowing only top-down grasps, which means that the robot has to figure out that it has to remove the other boxes before attempting to grasp the green one, because otherwise it will do collisions with the environment, and we want to be collision-free. And another possible environment was the cooking task, where the robot again had to take 5 objects from the one table, taking it to the sink, that it is the blue table, and then put it in on the stove, that it is the red one, and to be cooked. And some results to see some comparison to some, basically since we build on top of PDDL streams, we compared against the adaptive version of PDDL streams, that it is a version where it does some sort of optimistic sampling of objects through the streams iteratively. And as you can see, while in simple tasks, both our method and PDDL streams perform almost the same, or sometimes we may be a bit higher in computation time, since we spread up the computation due to the UCB. When the planning problem becomes more difficult, then you can see the difference in the decision-making time, in the planning time. And for example, when we solve the Hanoi tower problem, that it is also very difficult combinatorial problem, in the time budget that we were providing, the PDDL streams were not able to solve it, while the extended TAMP was achieved 99% success rate. So yeah, this was some of the ideas of combining basically Monte Carlo tree search, in some sense like a heuristic, in order to accelerate search on top of some top K planning in task and motion planning. And obviously, because of language models, we also got into this train, and we started actually quite some time ago looking into GPT-2. And of course, again, as I told you before, the idea was to have a human saying just a natural language command, a goal to the robot, and the robot to be able to reason about the scene graph representing the objects in the scene, and then being able to decompose this problem into sub-steps that it can solve, and then use, for example, a PDDL planner in order to solve them optimally. So we wanted basically to make our life easier and not search on very, very large planning domains, but making them smaller. So we wanted to rely on GPT-2 kind of language models to fine-tune them to output sub-problems in PDDL formulation. What we try to do here, we try to create a geometrically coherent natural language context that represents the scene representation, in particular the objects and their geometric relationships in the scene. We fine-tune GPT-2 into generating planning sub-steps in PDDL. Here we don't do task and motion planning, we're only focusing on task planning. And then we use classical planners to solve for the sub-goals. And in particular, we were using like fast downward for the solution of the sub-steps. So this is a very simple, small part of a graph of an environment. We were using the dataset of Alfred, that it is a simulator from NVIDIA that was providing us both with all the PDDL domain and PDDL problem descriptions and with natural language. So we could map goals to sub-goals, also to PDDL sub-problems. We're extracting from the simulator the graph that was representing all the relationships of the objects in the scene, and we are mapping it into some natural language representation that, though also explains the geometric relationships between the objects, and this was actually more compressed than what you see here. Like, for example, in the bathroom, closer below left sink, near below, etc. We compressed it into some very specific encoded relations that would be letters representing special relations, so that we can, because GPT-2 has a very restricted input size, embedding size, we had to basically do these changes. And basically what we did, we took the GPT-2 model, that it is a decoder-only model. We extended the tokenizer so that it can also include our prompt in particular, and we trained the language model so that we create what we call the RobLM, so the robotic language model, that outputs something like, as I said, sub-goals that are sub-problems of PDDL. Like, for example, if you want to put the soap into the drawer, you have to go to location countertop, pick up object soap, go to location drawer, put object soap drawer, which means you have to put it inside. So in a series of steps, the robot, that is not actually a robot, is an agent, is able to interact with the environment and solve this task. And as I said, we only do task planning here, and we rely on A-star search for doing basically the motion execution. But this comes also with some issues, as I will explain in a while. So here, and you can also find these results in the published paper, we tried to do something that I haven't seen many people doing. So we took the classical planner, we gave it the whole domain, everything that it needs, the problem, the PDDL problem, and we let it, with sufficient budget, try to solve the tasks and see if they are solvable per se, even as task planning problems. Of course, as I said, we were only considering an A-star search on the low level. It had issues because in Alfred, you really need to be on a very right location with respect to an object in order to put it, to grasp it, etc. So there were some failures that were coming from the motion domain, but we were not interested in doing task and motion planning. And we wanted to see if we say that this classical planner is the oracle, what you would like also the LLM to achieve with given the information that it has, is it able to do so? So no, it's not able to do so still. Maybe it's also because these GPT-2 models do not have the capacity to really do so, but what we found out is that the grounding is very, very difficult. So if we look at the results, we have here the plan actions. Maybe you want to look into the red and blue lines if they are visible in the screen, to focus maybe on those. With blue, it's the baseline, which is the oracle fast downward, and with red is the version of the RobLM that takes this scene graph representation that we created. And as you can see, in some they are quite good, not reaching exactly the performance of the classical planner, but they are quite good in planning action, so put, go to, etc. But when we put the arguments, they are very bad. And if we see also the subtasks, we can see that even with no context, the RobLM is actually quite okay if you just plan for specific subtasks. But if you try to do it as a sequence and you do one failure in one task, obviously you cannot go back requery. We could, but we didn't do it because we wanted to be fair in what we were comparing against. And yeah, as I said, even if we allowed the RobLM to try, for example, if the argument was apple, we were allowing it to try all possible apples that existed in the scene, because it is also another thing. In Alfred, there is a house environment, and there could be many apples. Like, there could be apple in the living room, it can be apple in the kitchen, and if it had learned that basically the apple should be in the kitchen, but the apple that was actually related to the problem was the one, I don't know, in the living room, maybe it would fail. So yeah, and another thing that it is interesting that we saw is that when we were giving at least the first argument, so basically the go-to location, it made the things easier sometimes. So here we are comparing against no context, against the context with a scene graph, but giving also in the input. Really? I have 5 minutes. Ooh, we have still the last part, and then I will speed up. Then we were seeing that, again, we are not able to reach this performance. So yeah, maybe now Niklas can talk a bit about how we can use optimization as guidance for learning for optimization, even if we don't have domain specification.
Okay, yeah. Hi, everyone. Yeah, I'm Niklas. I'm a PhD student also in Darmstadt. And so the task that we were looking into here is this problem of 3D robot assembly discovery. So the challenge is that you have to build like an arbitrary 3D structure that is like just sampled and presented to the algorithm. And you have to build the structure as good as possible with the building blocks that you have available. And yeah, we want to have it as a robotics problem. So all the time you have to consider the robot in the loop. And you also have to ensure basically structural stability throughout the whole construction process. And now the challenge of this problem is that you kind of have like a twofold combinatorial complexity, because on the one hand you have to figure out, okay, like where should the parts go best? And second of all, you also have to come up basically with a feasible sequence of execution. And yeah, we'll go really quick. I think Jeanette also gave a really nice overview that like one approach could be task and motion planning, which is very slow. And the other end is basically using some end-to-end learning approaches that basically try to directly map to like rather low-level actions. Nowadays, many works like basically use flexible graph-based representations, but I would say they are more limited in interpretability. And in a previous work that we had at Coral 21, we found that they are a little bit more limited in, or we observed limits in generalization. So for this work, we tried to make basically a combination of some graph-based reinforcement learning approach and mixed integer optimization. So the approach consists of 3 levels. On the upper level, you solve a mixed integer optimization, but it's a relaxed version, so you don't care about basically task sequencing, you don't care about stability, you don't care about the robot in the loops, you just want to basically get a prior information, like which actions do you want to consider. Then on the intermediate level, you run a graph-based reinforcement learning approach that basically benefits because the action space is already kind of compressed because you already have the information from the higher level. And yeah, then on the lowest level, you do a grasp and motion planning. So I think I will skip the high-level mixed integer approach. It's like, very simplistic, geometric, and what it basically gives you as an output, like the information of where should each block type go. And now on the intermediate level, you have to care about like all the constraints that you basically left out on the top level, which is the structural stability, robotic feasibility, and task sequencing. And to handle this, we propose an approach based on graph-based reinforcement learning, which basically you have the input scene, you transform it into a graph, where basically the nodes correspond to the building blocks and to the voxels that you want to fill, or the voxels that should remain unoccupied. Then you basically do like some rounds of basically message passing or multi-head attention, and you end up with an encoded version of the graph. And now you want to figure out, okay, which placing actions do I want to do? And you can do this by basically evaluating the values of the nodes which correspond to the parts that you can still place with respect to the nodes which are still unoccupied. And now the big advantage is because you first run this mixed integer optimization, you don't have to consider and handle like all the combinatorics that would in theory be there, but you can basically choose from the subset of actions, which is very beneficial and it really guides the exploration really well. And yeah, we performed 2 types of experiments. In the first experiment, we wanted to see, okay, like does this hierarchy really help us? So we compare the structured approach against an end-to-end approach and gave it basically the same computational budget, and we found that it basically doubles the performance. And the second experiment that we did is we basically asked ourselves the question, like in this hierarchical approach, does the mixed integer optimization all the job? And basically, is this intermediate level needed at all or not? And here we can also see that the intermediate level is really still needed to effectively solve the tasks. As you can also see in this video here, like because the placing space is like so constrained, it's really important that you sequence the actions well. And so for this, you really need this flexible graph-based reinforcement learning approach, because as you can see here, it really builds the structures nicely and does a good job in sequencing. And finally, we could also like transfer this to the real world. And so we concluded that this approach can basically provide first good results on this domain of robot assembly discovery. It is also invariant to problem size because you use this graph-based representation, so it doesn't really matter if you want to build a structure that is like 10 voxels big or 20 voxels big, and it also generalizes over the blocks, although they are rectangular for now. And yes, we just found that the structure gives us improved generalization compared to if you just try to do like brute force end-to-end from the beginning.
To wrap it up for today, I gave you some idea of how we used Monte Carlo tree search as for learning, for example, for approximating a Q function in order to speed up, as a speed up heuristic for task and motion planning. We looked into end-to-end methods that are not optimal for large combinatoric problems, but if you effectively guide them, we can see how we can better generalize. And finally, we also talked about LLMs that have a promise as some sort of high-level abstraction for task and motion planning, but the grounding is still a very big challenge. So I think that we have still a long way to go in this direction. So yeah, thank you for your attention, and I'm ready for your questions.
Thank you both. Anyone wants to ask a question, please come to the microphone. I'll start with a question. If anyone wants to come to the microphone, and meanwhile, please. So you mentioned that you needed our reward function for the tree search.
Yes.
What is the reward function and how hard it is to design it?
It wasn't that hard, so it had to do basically with the amount of basically penalizing for the horizon versus the success, or the planning success in simulation. So we had done some hyperparameter tuning, but it wasn't excessively. So yeah, you can find it in the paper. Is just two
It measures
terms.
the progressions.
Yes.
And if you have a nonlinear task, it would generalize to that? Like you need to make something worse before you can be better.
Sorry?
Like by nonlinear, I mean that like you need to, let's say, move away from the goal before you can move closer to the goal.
If it has experienced it and the Q function had experience that you have accounted for it, that it is a failure, and therefore you penalize the reward, then the Q function that it's the expected accumulative return is going to identify this, and therefore in the next round of the search it's going to penalize such action. So it depends, like if you have accounted for it, right, in your reward formulation as a penalty of if something happens that leads to task failure, even if it is some steps ahead, you should take it into account, and it should affect the Q function, because the Q function always looks into the future. Yeah.
All right, makes sense.
Yeah.
More questions? Well, I have another question actually. So in the LLM work, you mentioned that you had to retrain it. So how feasible it is to retrain a large language model?
It was a GPT-2, so it is very easy to train it in DGX. So this was one of the reasons why we couldn't go like higher. Not of course GPT-3 because we don't even have access to it. But we tried with Llama, and like currently also we were using Llama. It's still feasible. I don't know still if they have the capacity to fine-tune them effectively if we have the data still that are needed. So this is another question: how much data do you need in order to make it really generalized? And I think also how do you input the geometric information is still something that we need to consider. So I am more looking into this direction of combining the graph representation per se instead of linearizing it as language and feeding it into the LLM. But the capacity is for sure an issue in these models.
All right. Well, let's thank our two speakers this time.
Yeah. Thank you too.
So we have a short coffee break, and then we'll go on to our next speakers. So we'll be here at 4 o'clock.